All right, now I want to talk about a complete bipartite graph on P and Q vertices. So we denote this KPQ. What's P? P is the number of vertices in one set. Q is the number of vertices in the other set. All right, so I have two disjoint subsets of vertices. One has P things in it, the other one has Q vertices in it. And what's got to be true, any two vertices from each set have to be adjacent. And it also has to be what? It's a simple graph as well. All right, so it cannot have any loops or parallel edges. Any two vertices in the opposite sets have to be adjacent, which means I have to have a edge between them. So here are some examples of KPQ. Here's the first one, K10. So I have one vertex in one set, no vertices in the other set. That fits the definition because since I don't have two vertices, everything's fine. So there it is, K10. That's the complete graph, the complete bipartite graph on 1 and 0 vertices. It's only got one vertex. Notice as well that K10 is the same graph as K1. So K1 is the same graph as K10. By the way, I also have K01 where I have no vertices in the first set and one vertex in the other, and that's exactly the same. So what I'm saying is K10 is the same graph as K01 is the same graph as K1. All right, now let's look at K11. That's where I have one vertex in one set, one vertex in the other set. So I'm going to write all my vertices in one set over here, all my vertices in the other set over here. And the point is, I have to have an edge between everything from here and everything from here. So this is what K11 looks like. You will notice as well that K11 is the same as K2. Okay, what's the next one look like? K21. So K21, I have two vertices in one set, one vertex in the other set. Here's my first set of vertices. I have two of them. Here's my other set of vertices. I have one of them. And what do I have to do? Since any two vertices from each set are adjacent, I have to draw an edge between every vertex here has to go to every vertex here. So this is what K21 looks like. Get it? Now what does K2 look like? Or K22? Notice, so I have two vertices in the first set, two vertices in the second. I have to draw an edge from each vertex here to each vertex there. So here's one way it can look. Now, notice that I have edges crossing. But the question is, can I draw it without edges crossing? And if I can draw it without edges crossing, then it is what? Planar, to talk about a concept that we did before. Well, let's see if I can do that. So let's draw K22 another way. Let's put a vertex here, a vertex here, a vertex here, and a vertex here. And now I'm not going to change a lot of edges. Let's keep that one. And that one. And that one. So that all looks kind of the same. And now what? I just have to connect this vertex with the last vertex. And the point is I can do that this way. Let's try it again. And there we have it. So what I'm saying is, this graph really is the same as that graph. Kind of a funky looking graph. But here, do you see I've drawn it without edges crossing? So this is K22. This is also K22. This one has been drawn without edges crossing. That means, remember, I'm reviewing what it means to be planar. All right, so there's K10, K11, K21, K22. And there's the concept of what? KPQ, which is the complete bipartite graph on P and Q vertices. By the way, a complete bipartite graph must be bipartite. That's one of the requirements. But it need not be, and this is unfortunate, it need not be complete. It's as complete as you can get and still be bipartite. And if you want an example of that, look at this graph. The complete bipartite graph on 2 and 1 vertices looks like this. Notice it is not complete. Why? Because this vertex is not adjacent to that one. So a complete bipartite graph need not be complete, must be bipartite. It's as complete as you can get and still be bipartite. All right, so there's the concept of complete bipartite graphs on P and Q vertices. Now let's talk about closed paths. So what's a closed path? It's any path that begins and ends at the same vertex. So if I consider this my graph, here are some closed paths. Just the vertex V1, that's a closed path. It begins at V1 and ends at V1. Or I could go here, V1 to E1, which puts me at V2, then walk back E1, and I'm back at V1. So I go from here to here to here. That's this one, also a closed path. Another closed path is V4 to E4 to V4. Here I go E4, which is a loop, and I'm back at V4. That's also a closed path. So a closed path just begins and ends at the same vertex. If you want another one, this one right here, start at V2, walk along E2, go to V3, walk along E3, go to V2 again. That's a closed path. All right, so there's the concept of closed paths. Next is the concept of a simple path. And a simple path cannot be a simple path has no repeated vertices. All right, so I'm not allowed to repeat vertices, which means if I ever walk away from a vertex, I can never come back. What are some examples of simple paths? V1 up here, again, I'm looking at the same graph. V1 is a simple path. Why? Because I never leave V1. So V1 actually is a simple path, and it's also a closed path. But all the other ones here, these are not simple paths, because what? I started V1 and I go back to V1, so I repeat a vertex. Here's another simple path, V1 to E1 to V2, V1 to E1 to V2, just walk that. Here's another simple path, V1 to E1 to V2 to E3 to V3. So I go V1, E1, that puts me at V2, then I go E3, and that puts me at V3. Notice I do not repeat any vertex. So that's what a simple path means. Now there's the concept of a cycle. What is a cycle? A cycle is a closed path of non-zero length. So it's got to begin and end at the same place. Closed path. It should have non-zero length, which means I have to have at least one edge in there, and it's not allowed to repeat edges. All right, so I cannot walk across the same edge twice. So that's what a cycle is. All right, here are some examples of cycles. Now, I'm going to get a little lazy. You notice here, I'm not going to write the edges in here. Why am I allowed to do that? Because there's only one edge you could possibly walk on, and so there's no need for me to put it in. Oftentimes, one gets lazy like that when you describe a path. If the edge is clear, there's no reason to write it. So here is a cycle right there. Follow it. V1 to V2, to V3 to V4 to V2 to V5 back to V1. That's a cycle. Get it? Here's another cycle. V1 to V2 to V5 to V1. Get it? There's your cycle. Now, if you want an example of something that's not a cycle, if I go from V1 to V5 and then back to V1, that is a closed path because I do begin and end at the same vertex, but it is not a cycle. Why? Because I have to walk over the same edge twice. So there's the concept of cycle.